Hello. In this video, I am going to introduce the Metropolis Monte Carlo algorithm. This algorithm is at the heart of many of the programs we use to perform computer simulations of complex Hamiltonians. These programs can be used to calculate ensemble averages approximately. Furthermore, they will work with even the most complicated Hamiltonians. They thus underpin much of the current research that has been performed in this area. A problem from the point of view of this video is that the theory underlying the Monte Carlo algorithm is quite extensive. It is thus not possible to cover it all in detail during a 10-minute introductory video. To get around this problem, I will try in this video to give a summary of the overall structure of the arguments underlying this method. At the same time, I will provide links to various resources that will allow you to look into the individual topics that you will need to understand in order to understand the basis of the Monte Carlo algorithm. I would strongly recommend that you try to work through all this material and that in addition you try to write an essay in answer to one of the questions that you can find here on my website. Writing one of these essays will force you to structure all the ideas in this video and elsewhere on the theory underlying the Monte Carlo algorithm. Hopefully by writing this essay you will come to understand this theory better. On top of writing the essay, I would also encourage you to work through the exercises that you can find here. These exercises will take you through the process of writing your own Monte Carlo code to perform simulations of the Ising model, and will help you to thus better understand the Metropolis algorithm. Without further ado then, let's begin by summarizing the key ideas from statistical mechanics that we have learned about in these videos thus far. We have learned about microstates and phase space, and we have further learned that the central quantity in statistical mechanics is the partition function z, which is calculated by performing the following sum over all the microstates. We have seen how in some special cases this summation can be calculated exactly by using known series expansions. In many other cases, however, we cannot calculate this sum. Furthermore, we cannot even calculate this sum by brute force on a computer because it contains an enormous number of terms. There is a solution at hand, however, as we do not really want to calculate z. Z is, after all, not a physically measurable quantity, and so it is not as if we can compare the value we obtain for z with the value we might measure in an experiment. In fact, the only reason we have calculated z in the previous videos on the lattice gas, the Ising model, and so on, is connected to the fact that we can calculate ensemble averages by taking suitable derivatives of z. When performing simulations, we can thus just calculate the ensemble averages directly using the formula for an ensemble average, which is shown at the right-hand side here, and this is the ensemble average for the physical observable A. In this expression, the sum runs over all microstates. AI is the value of the observable A when it is in the ith microstate, and Pi is the probability of being in that particular microstate, which for the canonical ensemble is given by the expression shown on the right. Now, if you're paying attention, you're probably thinking that this doesn't seem like much an improvement on calculating Z, as A, we will still have to perform a sum over all microstates, and there are still an enormous number of terms, and B, we still seem to have to calculate Z, as we need this to calculate the probabilities of Pi. This realization might thus seem to have brought us to nowhere. Bear with me though, and trust me when I tell you that calculating an ensemble average will prove easier than calculating the partition function. As a first case in point, consider the expression that we have for the ensemble average here. There will be many terms in this expression that will have small values for Pi. That is to say, many microstates will have a relatively high energy and will thus have a relatively low probability of being occupied. We might therefore consider neglecting the terms that have a low value for the probability Pi when calculating the summation shown here. In other words, we might consider calculating the sum by taking only the terms in this sum that have high values for pi, as only these terms will contribute a considerable amount to the final sum. This seems like a good idea, but we immediately see that it is problematic, as how do we find the set of microstates that have a high value for pi? As we will see, it turns out that we can generate configurations in accordance with this probability distribution, but that to do this we will have to introduce a few additional mathematical ideas. The first mathematical thing we have to notice is that the quantity a in angle brackets that we are trying to calculate here is the expectation of a random variable, as pi is a probability. Let's suppose that we were able to generate microstates in accordance with this set of probabilities, the pi's, and that we were able to calculate the observables, the ai's, for these particular microstates. The law of large numbers and the central limit theorem tells us that the sum of these randomly generated variables would converge on the expectation for the random variable as shown here. Notice that in these expressions, the capital X underscore j's represent the values of the ai's in our randomly generated microstates. In addition, if we are going to be more mechanical about the nomenclature here, I would write the expectation as an ensemble average, like this. The EX symbol and the X in angle brackets symbol are equivalent. Physicists generally prefer the X in angle bracket, but statisticians prefer the E to the X symbol, which is why it is used in my other videos on statistics. Digressions about nomenclature aside, let's summarize the point that these realizations about the law of large numbers have brought us to. Essentially, we have realized that we can calculate the ensemble average of A by generating a large number of microstates at random in accordance with the set of probabilities, the pi's. When we add together all the values of AI that we get for our random microstates and divide by the number of microstates we generated, the law of large numbers and the central limit theorem tells us that the outcome that we will get will be a reasonable estimate of the ensemble average. Okay, great, you are probably saying, but how on earth do we choose random microstates according to these probabilities? Surely to do this, we have to calculate Z. To answer this question, we have to introduce one final piece of mathematics, namely the Markov chain. I teach a whole other course on Markov chains, and you will probably find that you need to work through some of the material in that course in order to understand what I'm about to tell you a little better. For the time being, however, we simply need to know that a time series of random variables is said to be a Markov chain if it has the property shown in the box on this slide. A useful way of thinking about this result in the context of statistical mechanics is to consider that the random variables, the capital X's in the expression here, are our randomly chosen microstates. We have a time series of these microstates, so the system is hopping between microstates. In other words, the positions and velocities of the particles that make up our system are changing with time. Now, these changes in microstate are random. Furthermore, the Markov property tells us that the microstate the system will move to in the future depends on only the current microstate the system is occupying. In other words, the microstate the system visits in the future do not depend on the microstates the system has visited in the past. We can construct models for many random processes by using Markov chains, as detailed in some of my other videos. Best of all, though, for the purposes of the Monte Carlo algorithm, certain types of Markov chain have the so-called ergodic property. This property is given in the equation at the bottom of this slide. In this expression, n is the number of microstates that we have generated in our Markov chain, and mi of n is the number of times we have visited the ith microstate. Consequently, the quantity in the limit on the left-hand side of this equation is the fraction of time spent in the ith microstate. The quantity on the right is dealt with in more detail in this video. For the time being, though, all you need to know is that this is a constant. The ergodic property thus tells us that if we use a Markov chain to generate a sufficiently large number of moves between microstates, the fraction of time we will spend in each of the microstates will settle down to a constant value. This realization is the central tenet of Monte Carlo sampling. The idea with this algorithm, in the context of statistical mechanics, is to simulate a Markov chain that has 1 over the expectation of Ti equal to the value of the Boltzmann weight of the microstate I, which is given by the right-hand side of the equation shown here. If we can set up the simulation in this way, we can ensure that in the limit of a very large number of steps, the fraction of time spent in the ith microstate will be equal to the Boltzmann weight of that microstate, by the result that we have just arrived at, the ergodic principle. As such, if we calculate the value of the observable A for each of the microstates that we visit during a chain, and we add up all these AI values and we divide by the number of microstates, we will get an estimate for the ensemble average. Furthermore, we'll be able to do this without calculating the partition function. In short, then, we can exploit the properties of Markov chains to calculate ensemble averages approximately. This really is the central message of the video. As I stated at the outset, you are probably going to have to look a little bit more into the theory of Markov chains in order to understand how all this works in practice. For the time being, though, let's move on and we'll look at how this works in general. In other words, let's simulate a Markov chain of microstates. The algorithm we are going to use here is known as the Metropolis sampling algorithm, and it works like this. We begin by generating a random microstate x1 of our system of interest, and by calculating the energy of this microstate using the Hamiltonian. In the slides, we will use the symbol E1 to indicate the energy of this initial microstate. We will then generate a random move of one of the particles in the system. There are various ways we can generate these moves, and the art of Monte Carlo sampling really lies in picking suitable trial moves. Regardless of how we generate the random move, the fact that we have moved a particle ensures that we have moved into a different microstate, which we will call x2. We thus proceed by calculating the energy of this new microstate. In the slides, we will refer to the energy of x2 using the symbol E2. We now calculate the so-called accept-reject criterion, pi, which is shown on the right-hand side of this slide. The value of pi is equal to 1 if E2 is less than E1. If, by contrast, E2 is greater than E1, pi is calculated using the formula after the comma in the square brackets on this slide. As such, if E2 is greater than E1, pi is always a number that is less than 1. Now comes the critical step. We generate a uniformly distributed random variable between 0 and 1, and we call this random variable p. If p is less than pi, we accept the move to x2, and we repeat the process of making a random move, but starting from the state x2 rather than x1. If, by contrast, p is greater than or equal to pi, we reject the move and go back to the microstate x1, and continue on by trying a new and different random move, starting from x1. Notice that as a consequence of the way pi and p are calculated, moves to lower energy microstates are always accepted. In other words, if E2 is less than E1, the move is guaranteed to be accepted. If, by contrast, E2 is greater than E1, then the move is accepted with a probability that is equal to the value calculated from using the formula after the comma in the square brackets shown on the slide. These two facts ensure that the algorithm samples microstates in phase space that have high Boltzmann weights. We never visit states that have low Boltzmann weights because all moves to these states are rejected. Lastly, note that when we calculate the final ensemble average for the observable A, we will add A of x1 if the move from x1 to x2 is rejected, and A of x2 if the move is accepted. Now, possibly at this stage you are perhaps thinking that this all sounds rather complicated. I want to assure you that it is not half as hard as it sounds. Honestly, the best way to understand it all is to write your own Monte Carlo code. And with this in mind, I have even written an exercise that will take you slowly through this process. Thank you for your attention.